Hey everybody, I'm wearing the Haslam shirt today, got the crazy looking beard. So hopefully can everyone hear and see me? It's always my fear when we start these streams that we're like last time we were on the wrong stream, today we seem to be on the right stream. I gotta shave this is getting crazy. How's everyone doing in the chat? How is everybody doing? Yes sir, you can see and hear me, that's awesome. Good to see you here, Aaron. Everything seems perfect, great. Good to see that. Good to hear everyone and see everyone online. Say hey in the chat. One thing I like to start class off with, hey Joel, hey Spencer, hey Jake, hey Will, hey Allie. So please say hey to someone in chat that's not me. Say hey to someone in chat that you see, who maybe you see in class that you haven't seen in a while. Amazing, good to see you. Mary, good to see you. Say hey to someone in chat. Give them an @. You guys know how to use that @ right here. Sorry the points aren't working. I was looking over the documentation as we were getting started here. I'll show you guys the documentation on it. I'm using... I've got, I don't think it's, I turned on the second one afterwards, but I'm looking over the Streamlabs documentation and everything, and there's where I was trying to give Aaron points right there, but it doesn't look to have registered. Let me search here. Well, I wonder if it put the points in. I can add points to Aaron, but, or anyone, I can add points to anyone, but it's just not, I don't know why. Streamlabs is modded. I'll look into it. I'll figure out what's going on. Yes. Million points right there. Everyone's saying hey to everybody. Where's Tyler? Oh no, where are they? That's a good question. So I'll try my points again. Don't worry. If my points show up, then points are working again. I don't know why points are being a little bit weird today. It started, you can have as many points as I want to. I think next time I might shave this into a beard, and then I might shave it into a goatee for the heck of it. I haven't shaved since I think like March 30th. Which is, I only guess 2.5 weeks. I feel like I should do the whole month, should do the whole month of April, but it's starting to get, it's starting to get to where I'm like, I can't handle it. It's starting to get like, I had one hair that was like bugging me, and I was like, mustache. You can't tell with the camera, but my mustache, I'll look at the camera and look all crazy. But my mustache is actually kind of blondish. I should, might be able to tell, but it's blonder than the rest of all this. And then I've got some gray across my beard, and I should just like shave and look better, but I was like, what the heck? We're not going outside for a while, so let's do this. Okay, so that's what's going on. Points don't look to be working. I'm very sorry about that. Oh, well, thank you, Will. I appreciate that. You guys are so encouraging. It's just, I was like, why not shave? I've never like gone this is about, I only did one other time when I was doing archaeology. I didn't shave for like a month because I was like just working outside every day. So we are talking about support vector machines. So we're gonna finish this semester. We're gonna do great right there. David's giving out 1,000,000 points right there, Will. But let's do it. Will, you get 1,000,000 points right there. Everyone's so positive. We love it. We start the class with some positivity, saying hey to each other, and that's what we do. Someone's commenting anything into a wonder, like, Brian, you having a mullet, and I'm like, yeah, it's kind of my hairstyle. I mean, it's long in the front too. Okay, enough about me, more about you. Let's hop into doing some support vector machines. We're going to do a little bit of a review here to start, and I think we're basically, if you look at the last assignment, it's on support vector machines, and you're on the last assignment now. And what we're trying to do is we're going to try to put out the take-home. I think we said you'll have 2 days to do it, 2 or 3 days to do the take-home. Please start early on the take-home. Don't talk to anybody on the take-home. You're not supposed to get help from anybody in particular. You're supposed to do all the take-home work yourself. Please, 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 please. We had a huge cheating scandal years ago. That's why we went to doing the coding nights, which we can't do this semester. But we went to doing coding nights because of a cheating scandal, which like disrupted graduations for people. So don't let that happen to you. One of our biggest goals with business analytics is that you have very strong coding skills. I was actually listening to someone recently, and they said that the tech sector, with the hiring of people with like skills, like in computer science, especially, they were talking about computer science, but I know we're not comp sci, but we are a technical skill degree where you know how to code, you know how to interpret analytics. So it's a very kind of sought after degree if you look at the field of business analytics. So do you know what days we'll be open for? We're going to put it over the days that's regularly due. And I think we're going to give, I can't remember what day we had it scheduled for, but it should be coming up here in about pretty much next week. So expect the coding night next week, and that'll put it away from the assignment, or we may be moving it back. I'll send more information about that. We're going to give you guys enough time. So I'll send more information probably this weekend about it. I'll talk to both Dr. Liu and Dr. Hylab or Hilafu, and I'll make sure you get enough info. Will it be base R stuff? Like, it won't be base R so much. It'll be more like training models. So you'll have to train a model. You'll have to use that model to make predictions. And so that's what you'll be looking at right there, is like making models, training models, predicting models. It'll be a lot of what we're doing at the end of this course. So you're just doing like predictive analytics, which is a huge thing. Predictive analytics is so crazy big. Will there be not so much a review. There'll be a review for the test, but I probably won't review so much for the take home. A lot of the answers are basically, we're talking about homework and being just for one person. Oh, no, not the homework. You can get help from the homework. You guys can still, don't send anyone your work. We don't want you doing that. But you can still talk to people on the homework. You can still ask each other things. You can still post around. Don't post your assignments. So that breaches the boundaries of what we think of help. But for the take home, you should not be getting help from people. You shouldn't be saying, how do you do this? You can ask questions for clarification, but for the take home, we really want it to be all of your own work. It's meant to mimic the coding night, and I know you guys, oh man, I miss coding night. Coding night is a very, very powerful way that we can analyze how good you are at coding. I mean, that's obviously what it's there for. And this is meant to mimic that. It's hard to do it as a take home because we want to make sure you're doing all of your own work and we trust you. It's just we've found things in the past where people posted it to message boards. Students reported that people were doing it in groups and stuff like this. So just don't do that. Don't do that. If you don't do those things, you won't have to worry about any of us worrying about that. Does that make sense right there? That the coding night is now turned into a take home, which we're looking at 2 or 3 days. I'll send more info about it to come, and you'll have, a good period of time to do it. It's meant to take you like 2 hours. So basically think of this. You basically have the coding night, but you'll be doing it on your own. And probably one of the biggest helps, if you're looking at a file to really know, if you want a file you should really understand, it would be the data mining with Caret. You'll see me do this all the time. I'll go to the data mining using Caret file. This is posted. You can find the data mining 3 using Caret. This whole thing right here, I know it's got tons and tons of code, but I can turn my eyes away and I can stop it right here and I can see what there is. Do parallel helps us use parallel processing, so it's just allowing parallel processing on clusters. We've got fit control here. This is setting how we're doing the k-fold cross-validation. That's just stopping the clusters right there. Do parallel stuff right there, so that's not really that interesting. We've got the results of a boosted models right here, so these are boosted trees right here. And then right here, we're looking at the percent of time, which is the accuracy because it's the mean. So understanding these codes right here, we've got the post-resample right here, which is going to give us accuracy and kappa. All the notes even really help you out. You get your ROC, which is your AUC, says it right there. And you've got your Y values right here, and you've got your Y hat values right here. The reason it uses the second column is it's just using one of the columns of the yeses and the nos. And thank you for the timestamps. I added them into the last video. Make sure to put those into the comments. So throw those into the comments for 1,000,000 points each. But you just want to be able to stop your code. I'm not looking at it and be like, okay, what's going on right here? Does anyone note this right here? This is setting all the whats for the model we're about to make. This is setting all of the blanks for the model we're about to make right here. 1,000,000 points who knows in the chat. This is setting all of the blanks for the model we're about to make. This is setting all of the different somethings for the model we're about to make. Who knows in the chat? Yes, Andrew, I'll take that right there. Andrew, why are you not a mod? You might be on another account. Let's see right here. Andrew, we will make you a mod. We're going to add mod for Andrew right there. All the parameters right there. Jake and Andrew, 1,000,000 points. Do you expect it'll be possible to make a perfect square on the... Oh, yeah, definitely. Probably, it might be even be easier because you can check your work. You've got more time. Tune parameters right there, 1,000,000 points. And I think we're going to do the final for like 2 days. More info about that. We want to give you as much time as possible because there could be errors, there could be internet issues, who knows? I mean, we've had crazy tornadoes. 2020 has just been, So, I mean, see, we're just off. Everyone thought it was 2012, but it was 2020. That's the crazy year. So what does it do in a final sentence? I'm confused. So what does it do in a final sentence? Oh, like, what does this code do? This code right here is going to store into an object GBM grid, which is we're using gradient boosted models. Good question, I have 1,000,000 points. So expand grid right here, all it's doing is doing all the combinations of these tuning parameters. So if we unhashtag this out, you can see that it's going to make a grid of all of the different tuning parameters. We have 4 different tuning parameters. We have, and this is good to review, we have 2 here. We have 3 levels here, and I mean the amount of levels. We have 2, and we have 3. 5 million point question. How many different models will this create? How many different models will this search through for this tuning grid? This tuning grid is all the different models we will look at, and we will, of course, use a fit control. 36, that's probably right. That is right. 2 times 3 is 6. 2 times 6 is 12. And there we go right there, 36. If you got that, you know it's correct. So there we go, 5 million points, all those answers. And there's the 36 models. So these are the things I want you to know like this, because then you understand that this is making a combination of all of these different tuning parameters, and it's trying out all different values of them. It's doing different amounts of trees, different amount of interaction depths, which is how many times we'll let each tree kind of grow. We have the shrinkage, which is the learning rate, and we have the number of min nodes in a number of min observations in node, which is the minimum observations in a bottom node. So it won't put like 1 down there. Well, it could put 2, 5, or 10, but that's the minimum it could put into a node. And these are gradient boosted models. And then you've got XGBoost, which I think has the 9 tuning parameters, which I know like 7 or 8 of them really well. There's always like 1 or 2 I forget, because extreme boosting is crazy, and you can just kind of play with the tuning parameters. We were looking at something last time. I want to show one more graphic right here. We were doing, did we go to the homework? Let me go and look at one thing right here. Where's the plot on this? Cool. So let's see. Hopefully I don't have anything that breaks the code. I want to show one important thing that I haven't shown in class nearly enough. I haven't shown this too much. Okay. DF not found. As long as the model runs, we're good. Error train not found, so I don't have the train. Did not create the train data. Let's see here. Let's make is train data not made. Electricity not found. Oh, I know why. This computer currently, I think, has the wrong working directory. It does, so we need to go here and go to downloads. Cool. I work out of my downloads. It's kind of in a classic Brian thing, work out of his downloads. But it's because the first semester I started using R, I would put my different classes, and then when I would have the different classes, it would create problems because you also have to switch. So maybe I should become more organized on this computer, like set a goal for myself. I will be more organized and keep this computer with the right working directories. But I always I can just put things into downloads. Okay, so this is the graphic I want to talk about just a little bit right now. This graphic right here, does anyone understand what this graphic is trying to tell you? Or does it just look like a bunch of rainbow colors and it's like, what the heck is this thing doing? Who thinks they understand this graphic and can interpret it pretty well and knows the importance of this graphic? So you can see we've got some mixing percentages right up there. That is your alpha right there, and you've got a regularization parameter, which is your lambda. So what the model I've made right now is a regularized regression using elastic net regression. So I like that entry right there. This is regularized regression through elastic net, which is a combination of lasso and ridge regression. Lasso is the one where we take the absolute value of the coefficients as a penalty, and ridge is the one where we take the square of the coefficients as a penalty. So what's going on with this graphic? Does anyone understand? Who thinks they understand? Just say yes or no for a million points. I want to get some thoughts from the class. If you understand, yes. If you don't understand, no. Like you have no idea what this graphic means. Or yes, I totally know what this graphic means. I know what it's trying to tell me. I do not understand. Kyle, you get 5 million for being first right there. We got another no in the chat. Not completely good. I'm glad to bring up this graphic because I know I haven't talked about it yet. It's just rainbow colors. Okay, so let's talk about what this graphic means. I like all the no's because I want. I thought I haven't talked about this. Once you know it, but the mixing, good. So what you see with this graphic right here, it'd probably be pretty hard to make if you had a ton of different tuning parameters. How do you judge the best line? Like if it's, so what we want to judge here, the best one is going to be this. I'm on the wrong screen. That's the best one. So the best line, there's really not a best line. There's just a best model. The best model is the one that was predicted because this is estimated typical miss the model will make on new data because this is via cross-validation. Cross-validation is how the model does on the validation portion, which is how we think it will do on new data. Does everyone understand what the RMSE cross-validation is? RMSE is root mean squared error, which is the typical miss the model makes. So if you remember back to 320, it's typical miss the model makes. Aaron for 1,000,000 points says lowest RMSE. So we want to have the lowest RMSE because this is a quantitative model. So I can infer from this automatically this is doing a quantitative prediction. And so RMSE is typical miss the model makes. I know it's on the validation because it says validation. So this is an estimate of how it'll do on new data. So the model that is the best is going to be this one right here because it has the lowest estimated RMSE. And so what do we have right here? We have the mixing percentage, and that's something that Andrew was asking about. Great question, Andrew. Said, what is the mixing percentage? Or kind of said it in so many words. The mixing percentage is when you look at regularized regression, which maybe, let me see if I can pull up. They've got different ways it can be written. Let me pull up regularized or elastic net regression equation. Let me see here if someone's written it out in a decent way. Yeah, this is a good way right here. Looks pretty crazy right there, but I'll show it. So this is one way to write it out, and I would never write it out like this. This just looks way too much complicated. Let me take a screenshot of it here. And let's, okay. Okay, so we're gonna go over here to a Word document. I'm gonna show you this equation the way they've written it. We will never write it like this. This is definitely not what we do when we solve it. This is like the old school way of you got to solve this by hand, you got to solve all this. This right here is the mixing percentage. So this right here is your alpha right here, and then you've got another alpha here. So what you want to look at is, and they've maybe defined their alpha differently such that, I guess, because 1 minus alpha, so if you put alpha equal to 0, I guess they're putting it between 0 and 2, are they? Because 1 minus, no, it'd be 1 minus 1. Oh, they're putting it between 1 and -1. That's what they're doing. That's an interesting way of doing it because they're defining, and so 0, does everyone see if you put alpha to 0, well then if alpha is 0, then this one's going to be over here. I would never define my alpha that way. Mixing percentage, I always think about, and I'll tell you why I would not define it that way. It's not the way R defines it. But it's just the mixing percentage of the amount of, this one's going to be ridge, and this one's going to be lasso. So this is ridge right here, because how do I know this is ridge? Why does Brian know via his memorization trick why this is ridge? 10,000,000 points. Can you remember how Brian memorized in his own head that this is ridge right here when this is squared? I use a little trick. When I see ridge, I see R squared, yeah. 1,000,000 points right there, Andrew. I think it's 10,000,000. Yeah, got it. So I remember R squared, and it has nothing to do with R squared. Ridge has nothing to do with R squared, but ridge has an R in it, so I remember R squared. So the one with the squared is the one we penalize for the estimates of the coefficients, because these are coefficients, and these are true coefficients, but we use estimates. And so we will penalize this one on the ridge, was what we call ridge. This one over here is lasso, and it's just the absolute value one. And so the alpha is the mixing amount of ridge and lasso. You don't have to know which way. We won't make you memorize. I mean, if you were to look at an equation right here, in this equation especially, if this were to be -1, then we would be doing all ridge. And then it doesn't quite make sense right there. I just don't like the way they've written it, but it does show that that's the mixing percentage. So going back to our graphic right here, what's going on with this is the alpha. The way I like to define it, is to define your alpha between 0 and 1. So 0 is going to be something like all ridge, and 1 is going to be like all lasso, where 0.5 is a 50-50 lasso ridge mix of using those two methods. Does that make sense with the mixing percentages? Like you're either going to penalize yourself all the way on lasso, all the way on ridge, or like a 50-50 penalty where you're like, well, let's take half of the ridge penalty and half of the lasso penalty. So the mixing percentage is how much of each of the different type of penalty you're using. If it's 0, then it's all of ridge, or it could be all of lasso. Does this make sense right here? Hopefully I haven't confused people. It's just like, imagine you're either going to have like chocolate ice cream, vanilla, or a mix of the two. So 0 would be like all vanilla, 1 would be like all chocolate, and 0.5 would be like a 50-50 mix of chocolate vanilla. So when we're at 0, we're just at completely one type of method. When we're at 1, we're at completely the other type of the method. And when we're at 0.5, we're at a 50-50. So at 0.5, it mixes it as in like the penalty we use is 50% of the alpha penalty and 50% of the ridge penalty and 50% of the lambda. So does that make sense? You could do like a 0.9 penalty, or 0.9 mixing, sorry. 0.9 would be like almost all of the one, but 10% of the other penalty. Does that make sense there, David? 0.9 would be like you're pretty much using just, let's say, maybe ridge, but you're using a little bit of lasso. Does that make sense? Cool. So it's like chocolate ice cream with just a little bit of vanilla. So the worst model here is all, I think so. Yeah, this one just, if that is all ridge right there, which absolute value allows us to get smaller. That's why people use lasso, because lasso, since it uses absolute value, will actually get some very small coefficients, I think. So there's pros and cons to each, and that's why we look at the difference. Because if you look at this one way up here, it never did any good, no matter what happened with the regularization parameter. So what in this, look at down here, regularization parameter, what in the way that they've written this code right here is the regularization parameter? Yep, you're right, Andrew. Oh, you switched to the other account now, I like it. What is the regularization parameter in this output right here, or in this equation? Let me see if it's working now. What is the regularization parameter in this equation? What is the regularization parameter in this equation? Is it lasso lets you get all the, I think it is lasso. Yeah, sorry, Jake, 10 million points. Jake, I think you're right on that. When you square them, they can get really, really tiny. That's what it is. When you square them, they can get like so tiny, and you can't zero out the coefficients. You're right. Absolute value lets you get them to 0. But when you square them, you'll get like these really, you'll include variables, and they'll be so small. They'll have coefficients of like e to the negative 23, and it gets ridiculous. So with lasso, you can get you can zero out coefficients a lot easier. And Andrew is right for 5 million points that it is lambda is the regularization. And look at what lambda is doing. I like the way the equation is written this way, at least at this part of it, because this whole thing right here, let's highlight it. Everything right here is the penalty. So if you set your lambda to 0, what are you just basically doing? If you set your lambda to 0, what are you basically doing? What are you doing? What do we call that in this class? We were just talking about ice cream flavors a moment ago. What do we call it if you set your lambda equal to 0? Just think you're timing that whole thing by 0. Whatever that is over there, you're just going to times it by 0. Vanilla, you're right, Andrew, for another 5 million. It's just vanilla regression. So you might hear the term vanilla regression or vanilla logistic. It means like no regularization done on it. It's just your common old, regular old logistic. And so this right here, if we set lambda equal to 0, and you can see we try that out. Let's hop back over to the graphic where we try out our lambda equal to 0. Everything all the way over here is with a lambda equal to 0. When you set the lambda too high, you're probably going towards like a naive model, because it's not going to take much information from the coefficients. It's going to take less and less and less and less and less and less information. So the regularization right here is controlling for the variance. It's going to take less information from the coefficients because it costs more. So that lambda right here is the cost for each of additional information we take. So if you look at it, this whole part of the equation is all about this information you're taking right here, the sum of the coefficients, either squared or absolute value. Last equals 1 and ridge equals 0, or vice versa. So, and I can't remember off the top of my, and so, Joel, expand a little bit, because the one thing I can never keep straight in my head is that, and I would not put this on the test. I will fight this question if it's on the test. I haven't put it on there yet, but I just know for certain that 0 right here is either all lasso or all ridge, and then 1 right here is either all lasso or all ridge. But it's like this is all of one type, this is all of one type, and as you go down, you get to the 50-50 mark, and then you start going towards the other. It's like all vanilla, a little bit of chocolate, more chocolate, 50-50 chocolate, more chocolate than vanilla, pretty much all chocolate, just chocolate. So if you were to say that this is ridge right here, you would say this is all ridge, this is with a little bit of lasso, a lot of lasso, 50-50 lasso ridge, this is with mostly lasso, this is with pretty much all lasso, this is completely lasso. So does everyone see how it's like a gradient? As you move across these lines right here, which I know kind of go in a weird direction this way, but you would go from being all ridge to all lasso, going from 0 to 1. And so you could have 0 for either one. Yeah, exactly. So 0 means that it is 100% the other. Does that make sense on what the 0 means? 0 means it's 0% lasso, or it could mean that. And if it's 0% lasso, it's 100% ridge. And then when you have the 1 right here, if it's 100% ridge, it's 0% lasso. Got it. That's awesome. And you should understand what these graphics mean, and that it's just trying the different mixing percentages. And this is all it's doing, is it's trying out all your different models. To go back to the code right here, which I think we have the code displayed for this one. We just need to look at the tuning grid for it. So here's the tuning grid, and you can see right here, here's the R part grid right here. And oh wow, that's not the right R part grid for this one. Because is that what we used? No, that's not the right R part grid. That's an R part anyways. Where is the... I lost it. Where are you at? So this is... Yeah, this is GLMNet. Good. We found it. Cool. I was like, that's the wrong tuning grid. And so here it is right here. If you look at the different gradients tried on this, there's 166 different models, it looks like, if I saw that correctly. But it's just trying all of these out right here with the alpha set to different values, and then it's trying it with different lambdas right here. And the lambda is the penalty. So very important stuff. I wanted to explain this graphic, make sure it was in the video and everyone knows how to interpret it. And this all goes to tuning parameters. And if you look at it, we literally were just talking about this right here. We were talking about just this one thing about what does this code do. And once again, it's all about knowing what your code does and not just running it. So please always slow down, look at your code, ask questions, email me questions. I appreciate everybody. Whew, it's been a crazy, crazy busy time. But let's hop back into those notes. So we are back. Now, we finished off last time here with support vector machines, and we were talking about how the support vector machine can take quantitative or categorical data. If you remember from last class, how does support vector machine, what does it do, or what does it use to find the equation? What does support vector machine use to find the equation it will use for the extra dimension where it can insert something? I'm going to ask all these questions. Support vector machine uses a certain trick, wink wink, to find an equation. Well, that'll have a kernels. It uses different kernels. So the kernel it uses can be different ones. It can use, so I'll find that slide right here. It can use different types of kernels, the linear, the polynomial, million points, all those answers in the chat, the radial, Gaussian base. And that's how it's going to decide this extra dimension it's choosing right here, which this is where we see our original data. So right here, looking at our original data where we have blue points and red points. We're doing a categorical model where maybe we want to predict if people are going to purchase a product. A decision tree could do this pretty easily. It would just, slice inside of here. I can't grab the graphic. Oh my gosh. Oh my gosh, there's a text box there? What? What happened? That was magic. I was like, the slide looked weird. But here's what the trick is doing. This right here, which I wish I could highlight. There we go, got it highlighted. That right there is the new equation it wrote. So it used a polynomial kernel to write this equation based on the x's. It's rather simple. It just did the square of it. And then all of a sudden when we plot it, we can insert this right here, which is going to be very hard for me to highlight. But that thing inside of there, that line, is the hyperplane. So we do this all the time, but it's very hard to visualize because if you have data like this, you then need to find another dimension. So I think this is the funnest and coolest thing about it, is that this data right now is how many dimensions, and it'll go to how many dimensions next. It is this many dimensions for a data set, and using support vector machine, it'll go up to this many dimensions. So support vector machine will bring it from this to this. 2 to 3, you got it. There are a million points, all those answers right there. It's going to go from 2D to 3D. And if you notice in the third dimension, which is all the way there at the top, it's all that equation over there. If you see, the third dimension is a polynomial equation based on the other ones. Now, these are problems that are easy to solve. Like we can kind of figure out these answers to these. It's like, oh, it's just going to make a kind of parabolic third degree thing right here. But this was using the polynomial kernel. So the polynomial kernel is solving out the best coefficients for the equation to bring it to this dimension to where we can put a hyperplane that creates separation. Now, Ivy, for a million points, mentioned earlier C. C is going to be something we can control where we have misclassifications. We also have an epsilon that we can use for quantitative models. So in the quantitative model, we have a cost parameter here, which is the epsilon. So the epsilon is kind of where we start counting the errors. If you notice right here, only these red lines right here are what are we going to count as a penalty. So we could move down the epsilon and we'd have bigger penalties, or we could move up the epsilon and we'd have smaller penalties. So you have the cost parameter, which is going to be, here's what the cost parameter looks like in this model. Got to go back and forth between slides. The cost parameter is here, where you can how many things can be in the margin. So this is our cost parameter with categorical SVM. And then the other one you saw was the cost parameter with quantitative SVM. Does everyone understand what's going on right here with the cost parameters, with the categorical model where things are caught and misclassified on the wrong side of the line right here, or the hyperplane, I should say. It is a hyperplane, it's just we can't see it in its dimensional world a lot of times. But you have this parameter right here that you can tune. So are the points outside the epsilon, the support vector machine, or the inner ones? The support vector machine is going to be, and I'll show the points, it's in one of the slides there, these 3 points right here. These are the support vector machine right here. It is just those points. So it's very few points deciding, oh man, don't you love we can zoom in? It's so easy to see things. So we have these 3 points are the support vector machine. So there's a lot of different support vector machines you can make because it's just going to be based on these 3 right here, and then it creates this parallel model right here. So you think about it, it's almost like this right here creates the distance, and this right here creates the kind of parallel line that'll be used. So it's really, I am 99.99999% certain it's always 3. Whenever we put the word always before a question, that's where I get scared to say, yes, it's always 3. I'm 99.99999% certain. Well, wait a minute. Maybe. Yeah, I'm trying to think. I'm wondering if it depends on dimensionality. Jake, if anyone figure that out for me. It'd be a really good theory question. And let's look right here. I bet you the support vector machine right here is based on 3 because it's going to be like these. If you look, it's often like 2 points of the same. And then, so it could be like these 3 right here. So, Myra squared, I'm 99.9999% certain, a million points right there, Andrew. I tried to prove you wrong about that the other day, but everything I found said you were right. Yes, Caleb! Caleb gets 10 million right there for trying to prove me wrong. I'm just afraid when we say always. Sure, you get the 20 million. I appreciate that, Caleb. I appreciate you looking into it. It's just when people ask questions like, is it always this? Unless I'm 100% certain, I don't want to say, because I'd hate for, I mean, I have been wrong on stuff. One of my favorite moments was when I taught this class the first semester and a senior in mathematics told me I was wrong on something and I really enjoyed it. He was like, actually, your definition of probability is more like da 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 da, but according to the so-and-so theory of such and such, and I was like, oh my gosh. So I've kind of helped my wording on it, tweaked it around a little bit. And yeah, that's our goal, is to be more accurate with everything we say. So please, 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 if you ever hear me say something you disagree with, tell me. I like people telling me they disagree with me in a constructive manner. If you're like, you're just wrong, Brian, you don't want to tell me why, I'd be like, well, tell me why I'm wrong. Explain to me the reasoning why I'm wrong. So this is kind of where we finished off last class. Says at least 2 support vectors. At least 2. Oh, send me information on that, Jake, and I'll read up on it. So yeah, send me information on it, and we'll take a look, and I'll even ask Dr. Petrie to double check. So support vector machine, I love it. I would just say this, I don't use it a ton. Probably my favorite is probably GBM or extreme gradient boosting because they're just like crazy powerful. Also neural nets. Neural nets are all the rage, which we'll be seeing at the end of class. It's just, I think sometimes support vector machine, it's just one of those tools in your toolbox. It's like really fancy. It's an important thing we should know. It's widely used. But who would think that you could take this data and somehow reorient it so all of a sudden it's got a linear relationship? That somehow some additional dimension, if you notice right here, we have x, we have y, and then we have x, we have a transformation of x. And if you look at it, we've made a transformation of x that creates some sort of linear configuration to this. So we used a kernel, whether it be polynomial, linear, or Gaussian, and we're not just getting a linear form from just the linear kernel. We're writing an equation of an x that is a transformed version of this x right here, making up some sort of equation with the mathematics from the kernel. So the kernel can be these choices right here that are somehow going to add an extra dimension to this original data set that will create a linear relationship in it. So it would be a huge trick question right here, but you don't have to use the linear kernel to achieve a linear relationship when you're adding an extra dimension to data. Does that make sense? Does that make sense for what I've just said? We are achieving a linear relationship by transforming the variable. The transformation could be linear, polynomial, radial, that's a Gaussian also, but it doesn't have to be a linear kernel for us to get a linear relationship. All we're doing is just writing a new equation down here. So you see the x transformed right there? That's a new equation of the original x, which allows us to put it into this new dimension for which we can basically do the hyperplane idea, which is going to create a linear relationship. So now we can look at here, we don't want these things to be far away from the line. And we can gauge this based on the epsilon. I think we're beyond the epsilon right now. Here we are. So the epsilon right here is the amount of which we'll penalize ourselves, or where we will start penalizing ourselves for how far things are away from the line. Does anyone have any questions? These are like really crazy things right here. That's like, who even thought of this stuff? That's why it's so cool. It's because like, I don't know who comes up with these crazy models. I know the other guy who came up with the perceptron. I'm trying to think of his name right now because we'll get to the perceptron here soon. But these models are super advanced. They're super just like powerful in what they can do. And we really couldn't be doing them without computers. So this is like one of the huge advances of computers. I mean, you could, but it would just take forever. So, and I feel like there should be, what is going on with these slides? So large values of C focus more attention towards the errors made by the model. Small values of C focus the attention towards the size of the coefficients. So just adjusting the C, why do we only penalize outside the epsilon instead of all of the residuals? And that's it right there. So Jake, amazing question, because what we have right here, I just want to think about it for a moment, or let us think about it. So look at this right here. If you put the epsilon really, 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 really high, you should be getting more models because you're going to create less penalty. But all of a sudden now, if you put the epsilon really, 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 really low, it's going to penalize more on bias. So what we see right here, large values, let's go to the small values of C, more attention towards the size of the coefficient. The result will be models that make a larger error. So if we put the C really, really small, which is the epsilon here, so if you make the epsilon really, really small, we're going to see models that make larger error. Does that make sense? Because you're going to allow models that make larger. Jake, that's it. Yep, this is the bias variance trade-off, 100%. That's completely it. And the degree to which the polynomial, we got all that right there. So it doesn't have much wiggle room, but that has a lower variance. So right there, variance is right there. So the higher C is going to create a lower variance. So C right here is inversely related to variance. So let's take a look at this right here. When you make the C, which is the epsilon right here, lower, you're going to allow models that have higher bias. Boom, we just figured it out. Does it make sense that if you make this smaller, you're going to have models with higher bias? So the models will have higher bias because we have more error in the models. And so if there's higher bias, there's lower variance. But if you make the epsilon larger, you will have lower bias and you will have models thus that have higher variance. So this is literally, as you just put it so eloquently, this is the bias variance trade-off. And how will you figure it? Cool, I like that right there. So you can just look right here, what is bias in regression? Regression bias is just how much we miss by. So bias in regression is literally this red area, which is how much we're actually going to count off ourselves from missing. So when we put it to a higher bias, we'll get lower variance. So high bias models have low variance, and all this good stuff right here, and low bias models have high variance. So we're just going to figure out the right amount. How will we figure out the right amount of C to use? How will we figure out the right C? Does anyone have any idea how we will figure out the right C? It literally goes back to what I started class with. It's this. When it says it'll be found via cross-validation, million points right there, Jake, you are right. This is how we do it right here. We do a tuning grid, and then we see how it works on the validation portion. So as it says right here, so perfectly on the slide, let's go back to the slide. We have here the polynomial kernel, or any sort of degree, any sort of thing used. If you look at the polynomial kernel, it has a tuning parameter on it right here, which is the D. So we have right here, we also have another tuning parameter right here. So whenever you're looking at these different tuning parameters on these, we need to put them through their own sort of cycle, seeing which values to use. So this, I believe, is the gamma. Let's take a look. And you see right here, any kernel-specific use, polynomial or gamma for the radial. Yep, that's gamma. So you'll see we've got the polynomial degree D, So there's the d for the polynomial degree, and there's the gamma for the radial basis. We also need the c. So you really only have 2 tuning parameters right now for the support vector machine. The linear doesn't have a tuning parameter because it's just a linear model. I guess you could, you know what you might be able to do? I think theoretically for 10 million points, could you include the linear model as in the polynomial? I guess you could. It'd basically be the same equation, wouldn't it? Could you somehow do the linear in the polynomial? It's only got one small difference. I don't think that'd make too big of a difference. Could you include the linear as part of your check in the polynomial? And how? I would believe that you can if in your tuning grid you just set d to 1. We should do lab. I think we'll do it tomorrow again. So we'll probably do lab tomorrow. So you could do d to 1 right here. I just like to make sure to have as much lecture as possible, make sure everyone understands all the concepts. So you should be able to set, so 1 plus linear raised to the d, yep. And then so we should just set it to 1 right there. I think we've done most of all this right here. So here's the different cost parameter right here. If you look at right here, we set the cost equal to 0.1, and we get a model right here that looks to be overfit. It's going really tight in there. And then we look down here. Yep, Kyle's right there, 1 million points. And then we put a cost to 10 right here, and we get this model that's underfit. So with the cost equal to 1, we get the model right here. It's overfit. We'll double check again. So we have here small values of C right here are going to have higher bias. Boom, right there. Small values of C, higher bias. Let's take a look again. Small values of C right here, and they're going to have higher bias. So when the cost is 0.1 right here, we see that this model misses a lot more, which is the bias right there. So everything is adding up nice and perfectly. We've got the E1071. I don't really use it that much. You can use this package to do support vector machine. We like to do it inside of like inside of train. So let's take a look at that here in a moment. Here's the model, and let's take a look at the train right here. So here we go with the linear and the radial right there. All this good stuff. And we've got the gamma tuning parameter and all this good stuff and the cost for the C. Okay, let's zoom in on these notes right here and see how to do support vector machine. And this, so Ivy, good question, with the activity, this should give some really big help for doing the code for the activity right here. Let's go ahead and I think we should be able to just take this and import it into R. And let's take a look at all of this code and see what it does. If we know what the code does, and I will say this, you'll notice that, and this is why I focus so much on the code, it's basically the same code over and over and over and over and over and over and over again. And so this one doesn't have a training and hold out. Let's do that. Let's grab a training and hold out. So we're just going to grab training. So let's train.rows. And there we go right here. We got this right here. Let's go back to here. Let's drop it in. We got body fat. So we are going to change this to body fat, and let's go body fat there, and there we go, and there we go right there. Whoops, wrong one. There we go, okay. So now we should have a training and a holdout sample right here. So we've created our training and we've created our holdout. And I'm going to make this look a lot better. Let's put this right here. That's just where we create our training and holdout. There's where we load the data frame. Here we are just using cross-validation since we are doing let's double check, a quantitative variable. We do not need to fit for accuracy, or we do not need to fit for AUC, because this is just a quantitative variable. We're predicting someone's body fat. So we go right here, we're making a grid for the support vector machine. The support vector machine is going to use the following variables. We've got right here the sigma, and we've got right here the C. So let's see right here. Let's go ahead and run this, and let's take a look at our grid. Here's our grid. Wow, 169 different models. 169 different models will be created. So the sigma right here is going to be for the support vector machine radial, and the C is going to be, and make sure it's a capital C. I want to pause on this. I have helped so many people on this who don't put a capital C. That is probably one of the biggest errors I see with assignments and with the lab, is if you don't put a capital C, and that's why I oftentimes like to copy paste my code. But I just remember all of a sudden it's like the support vector machine won't work, and it's because it didn't take the capital C. We've got here y tilde x comma data equals, so let's keep that right there. Then we have method, and then we have the training for the fit control. Verbose equals false, makes output less. We've got the grid being used. What is the smallest and largest value C can be? Great question. When it comes to C, we should be able to set it. If you look at this right here, how we're doing this grid, let's just take a look. Since we're doing a quantitative model, I believe C can be the smallest 0. And it wouldn't make sense. Let's just talk about two different models. So Caleb asked an amazing question. Because in this quantitative model, we're asking about where the boundary is of where we start counting off. So this one is quite different because, let's go to the notes right here. What we're trying to control is this boundary right here. So the smallest this boundary can be is 0. So, but the thing is how large the value can be. It can be up to probably infinity, but it's based on the size of the data. So you could go as small as 0, which is going to really kind of probably overfit the model because it's going to, if you look at right here, let's go back and look at it. So actually, I said it in reverse. It's going to underfit the model right there if we put it to 0. So we're going to get overfit models as we put the cost parameter way up because it's going to cost us more, and the model is going to try to fit a better and better model, a model that goes through it even tighter and probably goes to higher polynomial degrees. So we'd see that right there, that the cost parameter is going to find something that creates something probably really wiggly. So imagine that you're saying, this is how much it costs when you make an error, and so now it's going to make something like super wiggly to make sure it goes through it nice and perfectly. So going back to here, the cost parameter here is a little bit different on categorical models. So in the cost parameter here, you really want a higher C allows for more misclassifications, boom, right there, and lower C allows for less. And Andrew puts it so perfectly for this model. And so Andrew, the big thing you have to remember is that's when you're doing categorical models, and then when you're doing quantitative models, it's when you talk about where you're putting your epsilon. Will we be able to copy paste code templates like you do during class onto? Yes. You can do that for the take home. Yep. You can copy paste as much code as you want. We will not count you off for taking code we have given to you. So don't worry, we won't be like, oh, you copied the notes. No, that's what the notes are there for. That's what the data mining thing is there for. So you will not get points counted off for copying anything. You're welcome, Allie. Great question. Glad you asked it. 1,000,000 points, Allie, right there. And Andrew and Caleb and Kyle and Aaron. So the cost parameter that Andrew was mentioning is this one right here. So this cost parameter right here is where we start counting off. And as Andrew says, higher C allows for more misclassifications because more things can be in this boundary right here, where lower C allows for less. So you're going to see a little bit different. And this time we're going to get models that are fit a lot closer if we put the C even lower. So you're going to see this changes when you go over to here, because when you do the epsilon version, it's a little bit different. It's where you're going to start penalizing yourself. And so this is what we're working on right back here. How do I know this? Because it's a quantitative model. We're predicting body fat. So you'll also notice these are not whole numbers, because if we were to do a support vector machine for categorical data, it's how many misclassifications we are going to allow. So just even the way this grid is set up, it's literally just doing a grid, kind of being really fine at the start, and then letting it expand throughout. So we can take a look at how this is doing here in a moment, and we should be able to plot it. SVM not found. Oh no, I didn't make it. There we go. And it's making the model. This might take a moment. I should have let this run in the background while we're doing it. Support vector machine is not one of the quickest things. It's not one of the quickest models we have. So we should be able to make this, and we should be able to plot it. And we've got a forest grid there too. Oh, it worked. It got it. Okay, let's take a look at the row right here and see how it did. And I guess we'll look at a forest too. So all this code right here just tells you the best model. And we could look at all the results. Why not? Here's all of our results right here. You know what I like to do a lot of times? I like to take all my results, store them into a data frame, and then let's go to the data frame and just do this. Okay, there we go. Here's our best model right here. It's the same thing as we just did by printing the best rows. I just sorted it all. If you see, the best C right here is 56, and actually a higher C generally works. Does everyone notice this 4.0498? What you can do, higher values of C are doing a lot better. So why not just try new values of C? If I was doing this as my job and I had to find the best model, I'd look at these values of sigma. Sigma looks to do all right. It's around the 0.0001. So let's look at our tuning grid here. So we've got, and it was higher values of C. So let's change our C right here to just be the numbers. I'm going to totally change what's going on with this C. Let's see if we can get it below 4. Let's go 50, or let's do a sequence. It's not how you spell sequence. So it's going to be a sequence from, well, we can do it this way. From 40 to 150 by 5. And then when we go here to the sigma, I'm going to turn the sigma a little bit finer. It's a bad idea probably, because I've got way too many numbers now. And now we rerun it. So I'm just going to see if I can get it below 4, just to see what's going on with this model. So I put more values around where the good C's were. So I'm letting it do kind of a finer search to this. Does everyone understand how I'm manipulating my tuning grid now to kind of look at it and see what's going on? I could look at the graphic too. It's not the actual graphic, but I'm manipulating my tuning grid to see if I can get kind of some better looking results for this. My goal is to get a root mean square error less than 4. So let's go down here. Let's create the data frame again. And then let's go ahead and look at the data frame and see if we got an RMSE below 4. We're about at the same. And once again, you can get, we see a sigma there. We're not really getting below 4. And also the RMSE uncertainty shows us that probably not. If you notice, this is 4.0477. If you rerun it again, well, we do have a set seed on it. Let's try this one more time. Let's go here to 30. And let's change this to 0.1. So let's do that. I just really want to get, it's going to take like twice as long now because I expanded it. I really want to get below 4. It is using validation, so it could randomly get that. But I would focus in on this, and I would try to find the best possible model. You don't just do things one time. You create a whole bunch of different models here. You try to focus in on where it's working. It's like every time I'm doing this, I'm rebaking the cake. And I could reduce my grid. I could search in different areas. And I'm just trying to find the model that works the best. And we'll take a look at just the best model right here, which is what this code will get us. If you're wondering what the other code I was doing is I was saving it to a data frame, and then I was just sorting that data frame. I can still plot it and all of this good stuff right here. I think if we just plot the SVM, it should show us the results. Let's just check right here. Well, because we have the plot. Yep, it should just plot the grid when we do that. Let's hop back here. And let's take a look. Will it plot our results of it? Okay, let's see here. Yep, here we go. Cool, awesome. Wow. Does it? Okay, who else just thinks this graphic looks awesome? That is so cool. Who'd think you'd get these cool looking graphical shapes from this? Can anyone see where the optimum values of sigma are and where I should refine my sigma search? We're gonna do this one more time because this is the whole point of this. Be careful, because the optimum values of sigma are maybe not where you think they are. Where are the optimum values of sigma? Everything, yeah, this is not good right here. We don't want high RMSE. It's somewhere in here. Somewhere in here is the optimum value of sigma. And so I think it was something like that. Ali might have it from the output. It's close to 0. Andrew is right. So the optimum value. Now, this is just another area where it got good again, which is just kind of cool. It made this graphic. So sigma, we really need to refine our sigma grid down to these small values. So I'm going to go here to sigma, and I'm going to change what's going on with this sigma. And going off of that information, I'm going to put sigma down to 0.0001, comma 0.0001 and 0.001 right here, and 0.05 and 0.1. Okay, now we're going to redo this right here and see what we get. This one should go a lot quicker. It's got a smaller grid. I should have been looking at that from the start. It gives you way more information. And so we see our model runs. I probably don't need all those other. Cool, we got it. And here we are right here. So this is a lot easier to look at. And we might have finally achieved our objective. So here we are with the 0.05. The 0.05 is doing the best. I think that's the 0.05 line. Let me double check. No, that's the 0.01. So if you look at this, the optimum is the pink. Ali, you are right. The optimum is the pink. Great job, Kyle. 1,000,000 points also. The pink is the optimum line, 0.001. So now what I'm going to do is I'm going to refine my search grid again. I'm going to go up here to this, and I'm going to go to the 0.001. And do remember that these results might change, but I'm going to just use this information. I'm going to put here that this is the best for the moment. And I want to go and do a sequence. And let's go a sequence from this right here to, I won't do as many. We'll do that. from here to here by that. So it should be 10 lines. Let's see if we really see any differences now. This is the whole point. You know, like when you go to the doctor and they're like, the eye doctor, and they're like, A, B, A, B. All you're doing here is just searching. It looks like the biggest factor right here is sigma. Does everyone notice how most of the variation on these are due to sigma? So the sigma variation is highly influential in this model. So now when we take a look at this, we have a whole bunch of lines right here, and we still, it's due to randomness, but it looks to me, and it's very hard to see what the color line is. We could just use the code to find the best model. It's definitely evident that the cost parameter looks to be pretty good around 80. So does everyone see, like, cost parameter really looks to be good around 80? Like, we definitely want a cost parameter in this area. Like, they all kind of bevy out. That red one's not doing that same thing. But the rest of the lines are kind of going down around here. So I'd definitely set my cost parameter to this area. And I'd probably choose, I can't see what line it is. I'll just find the best model. So if I really want to see what the best model is, it's telling me I should use a sigma of 5e to the negative 04. So it chose one of the lowest ones. Is that the absolute lowest? So 5e to the negative 04. So don't you love scientific notation? So let's look at the grid real quick. So it's the 20th in the grid. So it's the 20th in the grid. And is this one right here? Maybe I misread it. So it is this model right here. Was it rounding it? It should be this model right here, it's saying. Or did it not say that? How's it reporting it? What are you doing, results? How do the predictions compare to the random forest? Great question. Let's take a look at that. So we're really not getting any below 4. You see, we're getting right at 4. And then we have the uncertainty right here. Let's look at the forest grid. So also I would optimize this forest grid. Let's take a look at how it's doing against the random forest right here. Ooh, does it beat the random forest? Who can tell me if it beats the random forest? It's pretty clear whether or not it beats the random forest. Let me show you the results right here. And you can look at those two results in tandem, and it should be pretty clear if it beats it or doesn't beat it. Which of these two wins and why? And I'm looking, yeah, the answer is pretty clear. Why does it beat it? Explain it to me in the chat. Pause the video if you're watching. But why am I, like, I would say definitely go with SVM right here. Like, it is a definite, we could try tuning the forest more, but why go with SVM? Is it within one standard deviation? I don't think it is. Here's this, and here's the standard deviation, which that's the smaller of the two. Here's, wait. Oh yeah, and then there's the forest, yeah. And then here is the RMSE here, and then here is the RMSE standard deviation here, which this is more than one standard deviation above it. Does that make sense? And it's more than one standard deviation. And does everyone see 4.03 and 4.32, the larger of the two standard deviations? Yeah, I know. No, my eyes, there's so many things on the screen right here that it might be hard to see. Let me run the two codes again. That should make it easier to see. At least it's all kind of a little bit closer stacked. It's just that it's not perfectly on top of each other right there. But you could take the larger of the two standard deviations, which is this one right here, and then these two RMSEs are more than one standard deviation apart. Does that make sense to everybody right there, that those two standard deviations here and here are more than one standard deviation apart? I mean, those two RMSEs, excuse me, are more than one standard deviation apart. So we do have evidence of a difference between the two models. Support factor machine looks to be working a good bit better. Now, what you could do is you go right here, change this to a sequence of numbers, and go from 1 to 20 and go by 1. And so now our forest grid is going to be a lot larger right here. So this random forest, then we're going to do a GLM net next. So we'll take a look at the GLM net. So let's see if this random forest works any better. We want it to be, if it gets close to it, I want to show you what I'm doing right here. What is 403 plus 0.16? What is that basically? 403 plus 1.16 is what? Someone just do a quick kind of number we can keep in our head. We've got some warnings. What is 403 plus 0.16? There we go, Andrew. I like that. That's a good number we can just keep in our head, that it's about 4.2. That's exactly what I was thinking. So now when we look at this right here, is it still, did it beat it out? Did it get close to it? Did it get close enough? Or are we still going with our SVM? Did it get close enough, or did we, or what do you think? Did it get close enough, or what do you think? And you see it's really you might not be able to see it from my head. So it's the forest is not really, it's not optimizing anywhere really strong. It's just kind of getting good around this point. We're still going with SVM because the forest is at a 4.31. It doesn't have a larger standard deviation, so we're still using the previous standard deviation. Yep, it's by more than one standard deviation. So we're still going with SVM at this point. SVM is still leading the way. And once again, I would put these all into a table if I was to present this. I would show all of the results in the table, but Forest cannot get as good as SVM right now. SVM is still one standard deviation above it. Maybe a boosted tree. Boom, let's do that. Well, we got GLM. Let's go grab some boosted tree after this, and let's do a boosted tree on it. Why not? We're doing review right here. So we've got GLM net, and I think we'll get to neural nets next time. So the GLM net, ooh. Oh, what happened here? Oh, this is interesting. The GLM net. And let's go a little higher on the GLM net. Let's go and put this to 50 and sequence from 0 to 1 by this. Let's put this to 0.05. We might be able to win with the GLM net. I'm doing this how I would actually do it, and then let me look at the results of this. The GLM net, if you didn't see it just a moment ago, was within one standard deviation, but the uncertainty on the GLM net was a lot higher. So I think it had a worse, just barely. Oh, I can see it up here, can't I? It's just a little worse. It's within one standard deviation, but it also had a lot of uncertainty, which I don't like that it has that much uncertainty. Like, that's way more uncertainty than we've seen in the other models. So at this point, I'm still leaning towards SVM. It's better, and it has less uncertainty on how it'll work on new data. But this one is within the one standard deviation. It could actually be way better. So it could, due to that uncertainty, be way better, but I kind of like my models to work how I want them to work. So this is a model up for choice. We could use it maybe. And let's do the GLM net right here. So let's plot it. And let's see how it looks. And whoa, you get so many interesting looking graphics. So if you notice where we need to focus our attention with the GLM net is right in here. Does everyone see? I'm going to refine my grid on the regularization parameter. So we are definitely going towards more vanilla. That's interesting. Why am I saying we're going towards more vanilla? Why is Brian saying this is more vanilla right here? I think I heard like random noises outside. Why is this more vanilla down here? Why is that more vanilla? Why is that more vanilla? Any ideas in the chat? Why is that more vanilla right here? It goes back to this. Because, this will be lambda right here. So this is the lambda. So the lambda is the regularization parameter. And so this is, we switched over now. Lambda is 0. Yes, lambda is close to 0. Exactly. There won't be a CP on this because this is not a tree. Trees will have CP, which is the complexity parameter, which is how large we go with the tree. So we can control complexity parameter to make a grid on that when we do the tree. So this one right here is what we started with, and it looks like I really need to refine my grid in here. So let's give it one more shot. Let's see, first off, how it did. It's getting lower, and ooh, look at this uncertainty. Man, it's got a lot of uncertainty. I don't like that. I don't like crazy amounts of uncertainty. That's not what I want. So we have to go to our lambda parameter here. And so what we're going to do is we're just going to change how lambda works completely. And we're going to put in a sequence of numbers just going in here and taking a look. We're going to go a sequence of numbers from 0 to 0.1. Yeah, that's where it's about at. By 0.001. So that should make 100 different examples of that, and so that's a lot of models. Okay, we'll let that run in the background here. So that's 100 different models. Why not make 100? Or it's actually going to be 300 models. Is that correct? No. This right here is 20, isn't it? Oh, that's a lot of models. Oh, it worked? Well, I'll be darned. Oh yeah, that's a lot of models. That is a lot of models. That is it's a lot of models. Okay. Oh, and then here's our results. So cool. Look at the intertwining of it. I mean, at least this is evidence to me that support vector machine can get lower because we're really not seeing anything better in this area. But I mean, I just love the way these graphics look. They're so interesting and fascinating. It's just like rainbow. But you don't need to figure out what's the best from this. You just need to go back to your results, and it'll tell you which one of those had the lowest right here. Jake brought up an important, so we want alpha equal to 1, so we're using completely either a lasso or a ridge, and then we want lambda equal to 0.014, but then here's what I really dislike about all this. We're still seeing a lot of uncertainty in these models, and I've not seen any of them go below, the 4, but that was our goal. So we're going to go to the data mining real quick. We're going to grab ourselves a boosted tree. So let's go to use right here, and let's go to GBM. Let's go to GBM. We're in selected. GBM grid right here. Wow, so much. So we've got the GBM grid, and I think we should be good. These are the boosted trees, and I think we might have some XG boost in here. And so we should be good on this. Oops, wrong button. We're over here. Let's go in, do this right here. Let's drop it in. Nicely written code. We've got our GBM. What's the only thing I need to change about my code? What is the only thing I need to change? And we've got the allow parallel true, because this uses parallel processing. So that's a small change right here. We're using allow parallel true. I need yep, Y variable, Andrew, 5 million points. You are exactly right. Great job following along. All I'm going to change is change this to body fat right here from birth weight, and we should be good to go. Let's cross our fingers. We're good to go. Of course we are. We had a problem one time. Oh, GBM already ran? Wow, GBM, you're great. So let's go ahead. I don't know why I'm copying that one. It's easy enough to write plot GBM. So let's look at our boosted model right here and see how it did. What did we call it? We just called it GBM. Let's capitalize though. There we go. So, oh, because it's doing the multiples. Yeah, cool. Okay. Looks like it didn't beat it out. We might need to increase the amount of stuff we're using. It's all caps. Nice job, Allie. Million points, Allie. I was like, what's going on? So here we get a report on multiple tuning parameters. But if you notice, we're not going below 4. So it looks like it didn't win. So I'm going to go here and I'm going to increase. Where does it look to be doing the best? Well, once again, we can go ahead and grab our results right here to figure out where it's doing the best. So we need to go in and go to GBM. And I ran just that. So where it's doing the best is with a shrinkage of 0.05. So I'm going to change my shrinkage grid right here to be a sequence from 0.1 to 0.7 by 0.1. So I'm making my shrinkage grid this right here. The interaction depth is 1. So we're probably good on interaction depth. You can't go in interaction depth below 1. So we can't make interaction depth smaller. Number of min nodes was 5. So I'm going to change this right here to a sequence of, it was 5. So let's go from 3 to 8 by 1. The trees was 200. So I'm going to change this here to a sequence on the trees. Sequence on the trees from 100 to 500 by 100. And number of min nodes in BIOS was 5. So we need to change. Oh, did I not change that one? Oh, I did. It's from 3 to 8 to 5. There we go. So I think we're good. Let's take a look at it right here. Here's our model. Did it really run that quick? I didn't think. Oh, because it's using parallel. That's maybe why. We've got a really good computer. Oh, that was. I didn't run the model. I just made the thing. Okay, so we should get this right here. This might take a moment, but since it's using parallel processing. But for anyone wondering, I hope I haven't lost everyone during the end of class right here. This is the real. Whoa. I love graphics. Oh, and it actually is readable. I thought it would be unreadable. Cool. Did we reach our goal? Oh, it's so close. Oh my gosh, the GBM did really well. Why is Brian excited about the GBM? And here's a hint over here. Why is Brian excited about the GBM? Why is Brian excited? I know, and it is probably going to come down to standard deviation, which model I choose. It's really going to come down to standard deviation. Why is Brian excited about the GBM? And these graphics are so cool. Parallel processing allows you to, I think, multi-thread. Parallel processing allows your computer to actually, if you have like an 8-core processor, double check everything I'm saying right here, but the do parallel allows for parallel processing that it can actually run quicker and faster. So any sort of algorithm that can use parallel processing is really going to optimize like what you're able to do with it. So GBM, since they're so labor intensive on your computer, my computer, since I think I'm using like a 16-core computer, really good processor on this, and that's probably why I'm able to do these at a decent speed, because if it's using parallel processing on a 16-core, like ridiculous computer, and so not everything in R uses parallel processing. So that's just computer being awesome type stuff. So if you're wondering why I'm excited about this, I'm excited because we basically got something really close to 4, which was kind of my goal. So let's see how well the model did with the best results. And did we do it? Oh, it's so close. Oh my gosh, I'm not happy with this. I am not happy. I am not happy. Why is Brian not happy? Man, that is crazy right there. I know, right? Andrew sees it right away. There's so much uncertainty in this estimate that this model that I've chosen is basically the same as pretty much every other model. And so I'm probably not going to go with this right here. And I think we should have some XGBoost in the code. So let's go grab an XGBoost model, because if you want to really boost things, go to extreme gradient boosting. So let's go here to XGBoost. And do we have XGBoost in here? Do we not have XGBoost? Boosted trees right here? Because there's that. We have it in the activity. Let me go grab the activity maybe, because I do not want to write out an XGBoost. So let me go grab the activity, and we'll take a look at that to end class, because I hopefully haven't lost everyone, but this is probably some of the most important stuff we've done all kind of since we've been in lockdown. Because literally what we're doing right here, if you can't tell, is we're doing every single... wrong thing. We're doing every single model and seeing how they all work and comparing them. And actually making informed decisions about which one to use. Right now, SVM, and you know what? I didn't even do all the other kernels on SVM. So I could have tried, I think we tried the linear, so I could have tried the radial Gaussian kernel. So I think it is the... let me go here. Oh, I had that up. I don't know where it's at. We might not do the boosted or the extreme gradient boosting. So I might hop back here, especially since we're running low on time. So probably some of the most important stuff you're seeing right here is the importance of graphics like this right here, that this is showing you all the models you tried via your tuning grid. Imagine telling someone in 201, when they're making just one regression model, that you can come in and make literally hundreds of models. If you look at my previous graphics, I'm literally making hundreds of models for somebody. Right here, I think I made thousands of models. I made like 2,000 plus models trying to figure out which model works best. This is data mining. This is what you do when you're searching for a model and you're comparing models. So in regression, in 201, we're just like, just make a linear model. But in data mining, you're like, let's make thousands of models and then compare all the models and see which model works the best. So you're literally sorting through tons and tons and tons of models. And then what we will do is we will see how the model actually works on the holdout. So I think what we did is we put all our money on the SVM, right? Didn't we do that? So what do we have to do now since we put all of our money on the SVM? Which I have not done yet. I need to hear this in the chat. We've only got 3 minutes. We'll go for another like 5 or so. What do we need to do that we put all of our money on the SVM? We put all of our money on the SVM. Try it on the holdout. And once again, nice job right there, Jake. You million points. You well earned that right there. We're going to hop right back here. We're in the data mining. So if you notice right here, we can use, I think it's the resample one, the proc resample. So if you look, we can just grab this post resample. This code, I wrote it out last time. I was doing the RMSE last time by hand, but why do it by hand when you don't have to? I'll show it by hand again to show it confirms the answer. But we've got the post resample code right here that takes the Y value and the predicted Y value. So let's go back to our untitled sheet right here. I think we're using the SVM. Did we call it SVM? So we just got Y comma Y hat right there. Yes, we've got our SVM right here. And then what we want to do, or first we want to take on the holdout, we want to take someone's body fat on the holdout, and then we want to take the predictions from the SVM. So we want to do predictions from SVM on new data equals holdout. There we go right there. Are we happy with this? Are we happy with this model right here? Am I happy with this result or not? And if you can't remember, let's show what the result was on this. Am I happy with this result or not? If you couldn't tell from my face, if Brian is happy or not. Yes, I'm very happy with this result. It did do worse on it, but not that much worse. It did only a little bit worse on it. And you notice right here, we've got the RMSE, and we got the RMSE right here, the typical miss. I'm finding it interesting that the R-squared is actually higher, but we usually use RMSE. It has to do with probably different residuals that were in it, and the RMSE standard deviation. Now, once again, last time I actually wrote this code out by hand, but you can use the post resample code for it. I've just written so much code by hand, I'm used to writing it by hand. We could look at our other models, but I did decide on this model, so I probably shouldn't like go around and start looking at my GBM now. But GBM had a lot of variation Ooh. Is Brian really happy right now that he went with his SVM? I said I'm going with SVM. I'm sticking with SVM. So if you look, the GBM had a lot of variation in how it would work, and that came to bite us right here because we had a lot of uncertainty of how it would actually work on new data. If you look back on the GBM results, the GBM had some of the highest standard deviation right here. When you look at this is your uncertainty because we're like, well, here's how we think it will work, but we could be off by this amount. If you notice, was this prediction, now be careful the way I ask this is some of my last questions, was this prediction for the RMSE fairly accurate given the standard deviation on it? Was that prediction for the RMSE fairly accurate given the standard deviation it reported to me? Was that prediction? Yes, it was, because you'll notice this right here is within one standard deviation for how the model will work. We think it will miss by about this amount, but we are uncertain by about this amount here. So these are huge concepts we've been covering right here because literally we just data mined this question. So we found the best model for this was the support vector machine. So we went through, we did a boosted tree, we did regression, we did regularized regression, we did just a forest. We didn't do a single tree, but I mean, trees beat forests. So if a trees are going to beat forests most of the time. Forest beats tree. So forests are just more trees, and they'll have a better chance than just a singular tree usually. I don't think I've ever seen a single tree beat a forest. So forests are just more labor intensive, and trees you can actually look at. So if you want an interpretive model, you might use a tree. It's like the big pro and con between trees and forests. Forests are more labor intensive. Forests usually do better in predictions, but trees can actually be looked at individually. How's everyone doing? Did this all make sense? And maybe did this help unify the class a little bit to you at the end of this class of what we've been doing? Because literally for the last 20 minutes right here, we've just been doing the different models, how they work, and how we can look at them and see how they compare. I feel like this has been a very, very important part of what we've been doing because this like unifies, at least in my mind, what we've been teaching. So I think that does it for the notes. So good stuff. Yes. I hope everyone got really quiet and I was just getting really excited as we were going through. If you look right here, example of SV Poly. So you know what? One model is going to come out here to try at the end to help out. I think we did the Gaussian kernel. Okay, so let's try this. Or did we? Let me look at the last bit of code we did. So we were looking at the, where's the SVM model on it? Train SVM radial. We were looking at the radial Gaussian. Okay. So we got one last model to try here with our last little bit of time. We've got the radial, the polynomial model. We've got the polynomial degree. Okay, so this is the last model for us to try today. That helped. It was so nice seeing you. Yes, you're welcome. Going through the boosted tree. Awesome. And I like the boosted tree's plot. It just really shows it in a cool way. Y tilde x comma data equals. And then, wait, what's going on? Why is there a birth weight? Oh, haha, that wasn't a comma. I thought I hit enter on the comma. Verbose equals false. Turns down the output. We've got here our tuning grid. We've got here center and scaling to turn stuff into z-scores. Yep. Thank you, Andrew. I'm so glad that helped. That's what I want for people. We've got the degree of the polynomial. We've got the scale right there. And there's your different tuning parameters right there. So we're good to go. And now we got to change this to body fat. And let's do this right here. Birth weight not found. Cool. Because it's train data. Forgot to enter that in. We're good to go. We'll take a quick look and see if it's even getting close. Watch it win. Watch it win out. And I'll be like, well, should have went with the... so would I have chosen this one? SVM right here. It looks like a no. That looks like a clean no. If you look at... I don't know. That's at a bigger scale. And I really need to refine this tuning grid. Degree 5 by 0.2 by 1 by 0.2. Okay, this will take a moment right here. Wait, this takes a moment to tune grid. Okay, so we're going to go look at the best result. Let me get a thing for the best result right here. And let's go right here. And let's drop that in. And let's see. Okay. So all we're doing right now is just running the code. And let's take a look at what it does right here. Oh, we've got it. So we'll be good. Let's plot it. There's our different models, ridiculous amounts of models. Oh my gosh. The scale on the RMSE is nuts. But let's see what it found. It found, did we achieve it? Yeah, I wouldn't choose this one. Why would Brian not choose this? Why would Brian not choose this model again? This would not be my #1 choice. But it is it is within one standard deviation. It might even be the best, but high uncertainty. Yeah, the high uncertainty I don't really like. So all we're going to do is go grab our post resample right here and just drag this code down to here, drop it in, grab the predictions from the SVM now, and I think we just overrode our previous SVM. Yeah, and look at that. It's bad. So yeah, once again, this would not have been our best choice right here. Our best choice was the original SVM we did. So, sirens outside. So if you notice, we really settled in on a really good model. So I think we made the best choice. And why did I choose the model I did? It had the best RMSE. It had the least amount of uncertainty, which you don't have to choose the one with the least amount of uncertainty. I just, especially seeing nothing could get underneath 4. Sorry for the sirens outside. Seeing that nothing could get underneath 4, I was like, I'm going to go with the one that's pretty certain for what it'll do. And then how did it do on the holdout? It did pretty much as we expected it to do. So that's got it. That's the unifying theory of everything for the class so far, especially when it comes to all of this. There's the AUC and all the probabilities, pros and cons. I'll let you guys read through. But all of this right here leads us to neural nets, which is going to be absolutely crazy next time. So expect some fun. We'll do neural nets next time. I think we'll do a review last. But hopefully this unifies everything. Everyone, have a great day. Swing by after 5 if you got questions. But we just did pretty much all the model making we know so far in this notes right here. And maybe, you know what I'll do? Who would like it if I posted these things right here? Would you guys like it if I posted this example we just did? You're welcome, Jake. Let's go here to File, Save As. And let's just go all model testing example. This really, yes, post this, you got it. So I thought that would help out right there. This really, and I'll put it under the modules. You'll see it under the latest module for data mining 6. I'm going to put it in data mining 6. So you'll see this right here. And you can play around with it more. I will give 20 million points if someone can break 4. If you can break 4, now don't spend all night. No, why not? I will max you out on extra credit for the first person who can get under 4 in your, you have to get underneath 4 with your model, and then it has to get underneath 4 for the holdout. So it's such an arbitrary boundary. But that is your goal. I will max you out on extra credit if you can get underneath 4 for when you see how it does on the validation, and then on your holdout. Yep, I'll be here tomorrow. We'll work some lab. Standard deviation doesn't matter. It just has to get underneath 4 on your validation. So your validation has to be underneath 4, and then on the holdout it has to be underneath 4. So probably you want a small standard deviation if it's underneath 4. But even if you luck out into it, I'll give it. Like you could just start messing around with it and luck out into it. I'll still do it. You have to somehow put a set seed in. You literally probably just generate enough seeds to get lucky enough. I don't know. We weren't able to break 4, and it kept just hitting a hard boundary, it seemed, of like 4.06. But give that a shot. I will max you out on extra credit. I just want you guys to maybe play around with this a little bit, because that's what you do when you make models. You just make, I mean, I probably made like 5,000 to 10,000 models. And imagine telling a 201 student that, like, in the last 30 minutes of class, Brian made 5,000 to 10,000 models. Cool stuff. Yes. Could you do that? Jake, see, there might be a way to do that, but I want to point something out. That is not good statistics. Finding a seed that gets you a good result is not really good statistics. But I will still allow that just for the fun of the challenge of it. So even if you use what I would think are bad statistical techniques, I will let you guys have fun with it. I just want to see if it can be done. And hey, you know, if you want, start looking at neural nets, because maybe a neural net could do it. Or here's a big thing. This is the last thing I'm going to say, and then I need to hop over to 201. Then I'm like, where the heck is Brian? Methods in train. If you want, take a look at this and here, and I would really, once again, this is the well-earned points of it. Playing around the seed, yeah, might get you the answer, but here's where it gets crazy. Right here, something in here is probably better, and I don't know what it is. But these are all the different methods you can use, and I can just keep scrolling. There's hundreds of methods, probably about 200-300 maybe. But here's all the different methods you can use inside of train. So if you want to check out one of these methods right here, least square support vector machine, sure, that's something we'd like what we did. It's got a regularization parameter here, so it's controlling for bias variance trade-off. Can I post that link? You bet. Of course, you got it. So check this out right here. Go around, drop in the chat, you got it. So check that out. Try different things if it works. Yep. So give it a shot. And this is the real power of data mining, is when you can just like, And here's the thing. I want to point something out. Gosh, you guys got me so excited about all this stuff today. What you can do is once you write all this code, you could literally just make it where you could define your y variable and run all these models and then compare all of them. Think about, if I'm going to do this for my job, I'm not going to rewrite all this code every time. I'm just going to set it up and then let it run through these different models. I might just run it overnight and have it run 100,000 models for me. So, I mean, you could just define your y variable, have it run all these different models, and then do a report for you, and you could print it to an RMD, and you could look at all the different, models and how they worked, and then refine your grid. You could even write a loop that refines your grid for you if and it could narrow in. So you could loop things to refine grids. You could do so much. So anyways, everything I've done right here, you could literally just click a button and run it overnight. But I have to off to the other class. I got 5 minutes. I'll see everybody later.